So it is also possible sometimes that the feasible region is empty. So for example, if I have constraints like I had earlier, 2x1 minus x2 if I have a constraint x2 less than equal to 0, then this system of constraints is infeasible. So we say that the system is either inconsistent or R is infeasible. I'm sorry. So we say R is empty or problem is infeasible because there are no points which actually satisfy every constraint. So sometimes this inconsistency or infeasibility arises because of a single constraint. So for example, if we have a constraint like x3 square less than equal to minus 1, so this would clearly be infeasible. Okay, but other times it is the combination of constraints which makes the problem infeasible. For example, the previous system that we wrote. So it's easy to see why it is infeasible because if x1 is more than 1, then this term is always strictly greater than 1, and this term, including the negative sign, is always greater than equal to 0. So if I add all these three numbers, I will get something more than 2 on the left hand side, whereas the right hand side is constrained to be 0. So we say that the problem is infeasible. We don't say that the constraints are infeasible or R is infeasible. We say the problem is infeasible. Okay. So in this case, we can't really find an optimal solution because no such solution exists, even though the functions are all very well defined. It's not that these functions can't be evaluated in the feasible region. They are very nice functions. These are linear functions, and my objective function is also a very nice function. It's a convex quadratic with a positive definite Hessian, but still there is no solution to this problem, and this may happen. Okay, it's easy to see that if a problem is infeasible, changing the objective function alone cannot make the problem, make the region, make the problem feasible. Conversely, if a problem is feasible, that means my feasible region R has certain points. If I change the objective function, the region R is not going to change. Okay, so R depends on constraints only. Okay, it is independent of the objective function. So note that our problem could never be infeasible if we didn't have any constraints. So for unconstrained problems like we have been looking at so far in the course, the problem is never infeasible. You can pick any point and that will give you some function value, and you can try to improve by finding better points around that point. In the constraint case, we have this additional complication of how to even find a feasible point. Even that is not very straightforward. Other problems also arise when you have constraints. My problem could be unbounded. Okay, so this is possible even in the case of unconstrained problems. If f can take arbitrary low values at some feasible points in R, in your feasible region. Okay, so notice that this R is different from the R we use for denoting the real numbers. Okay, so this denotes the set of real numbers, but a simple R denotes the feasible region. In the unconstrained case, these two denote the same set, but in the constrained case, they are very different. For example, log of x when x is greater than or equal to 0, because as I come closer and closer to 0, my objective function will start approaching minus infinity, so this problem is unbounded. Sometimes the problem becomes unbounded only when x takes very large or very small values. So example, minimize minus 3 x1 subject to x1 greater than or equal to 0, and as x1 takes bigger and bigger value, the objective value keeps going down and down, so this is unbounded because it can go to minus infinity. and for the objective function to go to minus infinity, x1 really has to go towards plus infinity. Okay. We say the feasible region R is bounded if I can draw a sphere of finite radius around R. So if R is a subset of the set of points which lie in a sphere, so where k is finite. Okay, so geometrically, if my feasible region, suppose my feasible region is denoted by the shaded region, then this is bounded, and essentially there are two constraints. Since I can draw since this region can be enclosed inside a circle of radius r. I'm sorry about my drawing. So this set is bounded, and you can see that if the feasible region is bounded, then the variables cannot go to infinity. Okay, because this inequality makes sure that x's cannot take infinite value. So any component of x cannot take arbitrary large values. Okay, and this part is somewhat important because for certain types of problems we will be able to say that the problem cannot be unbounded, so either it is infeasible or it must have some solution. Okay, so it is possible that R is bounded but the feasible region but the problem is unbounded. I'm sorry, but so what I'm saying is it is possible that the feasible region is bounded but the problem is unbounded. So for example, again minimize log of x, x is between 0 and 1. So this is a way of writing two constraints in one. This essentially means that x is greater than 0 and x is less than 1. If we want a single component, I'm in R1. So clearly x1 is bounded. I can draw a circle around this region, but log of 0 goes to minus infinity.